Hi everyone, here myself Nishu Mittal. I'm going to present second assignment of course CML 7 to 6. This assignment consists of two parts. One is to be performed by using Orca software and other is by Crystal Explorer. So let us discuss it one by one. So first I will discuss the assignment performed by Orca software, and all the calculations are performed by using DFT with B3 631G DP level of theory. And let us start. So first of all, we optimize the geometry for ethylene glycol and acetone. As we can see here in figure 1, this column converge yes. So this confirm the convergence and geometry optimization for ethylene glycol, and the figure 2 represent the energy profile correspond to ethylene glycol, and which also give us an idea about the optimization step number. Similarly, figure 3 corresponds to the convergence for the acetone, and figure 4 give the energy profile diagram for acetone, and similarly it also gives an idea about the step number which optimize the geometry for acetone. And this figure represent the corresponding optimized geometry for ethylene glycol, and energy is to be noted is minus 230.250862 Hartree. And for acid, this is the acetone geometry optimized, and energy corresponding to this is minus 193.164211 Hartree. And these are the tables correspond to ethylene glycol and acetone respectively, which show the bond distance, bond angles, and dihedral angles. Here we can see that R12, this parameter represents the bond length. If R12, this means that this is the bond length between the atom 1 and 2, and the atoms are labeled in this figure. Similarly, A214 here means the angles formed by the atom 2, 1 and 4. And similarly, the D4123 here means the dihedral angles formed by the atoms 4, 1, 2 and 3. And similarly, this figure represents the bond length, bond angles and dihedral angles present in acetone respectively. Atoms are labeled in both ethylene glycol and acetone. And the dipole moment noted for ethylene glycol is minus 1.393400 dBi, and for acetone it is noted as minus 2.829400 dBi. And then we calculated glycine IR spectra. This is calculated by software and this is noted experimental. And the peak positions almost match, so it will well agree with the theoretical spectra. So there are two major groups in glycine. One is NH2 group and other one is COOH group. So generally we observe the peak position corresponding to these two main groups for study of the IR spectra for glycine. And then we optimize the geometry for 1,2-dichloroethylene for the cis isomer as well as for the trans isomer. This is structure corresponding to cis isomer, and energy was minus 991.019621 Hartree, and this is the structure of trans isomer, and energy noted corresponding to trans isomer is minus 991.023036 Hartree. As we can see that energy corresponding to the trans isomer is more negative. So trans isomer is more stable as compared to cis isomer, and energy difference in both the structure is noted as minus 2.14339 kilocalorie per mole. The reason for the stability of trans isomer is that there are two bulky groups in 1,2-dichloroethylene, two chlorine atoms, and in the cis isomer both the chlorine atoms are on the same side. They causes steric repulsion which causes the instability, but in the trans isomer both the chlorine atoms are on the opposite side, so they do not cause any steric repulsion, so the corresponding structure becomes most stable. And next we optimize the geometry for butadiene. This is the structure corresponding to the ground state geometry for butadiene. This is HOMO diagram for butadiene, this is LUMO diagram, and this is HOMO-LUMO combined, and this is the HOMO-LUMO energy level diagram corresponding to butadiene. As there are 30 electrons in butadiene, so any one orbital can contain only 2 electrons. So there will be 15 orbitals. So 15th orbital is HOMO and the 16th is LUMO. Then we optimize the geometry for ethanol and DMSO, and then draw their electrostatic potential maps. Electrostatic potential maps are graphical representation of the electrostatic potential generated by molecules charge distribution. These maps combine molecular structure with color coding to visualize how the positive and negative charges are distributed across the molecular surface. As we can see in case of ethanol, electron density corresponding to oxygen is highly distributed. So this represents the most electronegative region and it is denoted by the red color. The hydrogen in the OH group is partially positive because it loses electron density to the oxygen, create a positive potential region around the hydrogen, which is shown in the blue color. And the carbon-hydrogen bond in the methyl group are relatively non-polar, meaning that electron density is evenly more distributed. This region appear green in the ESP map, indicated a neutral. And similarly, in case of DMSO, the oxygen is highly electronegative, withdraw electron density toward itself. So it consists of highly negative potential region, which is shown by the red color. And these are highly electropositive region shown by the blue color. And this is generally the neutral, which is shown by the green color. And these are the partial charge distribution diagram for ethanol and DMSO. So let us go with the next part, which is to be performed by the Crystal Explorer. We are given with the 2 polymorph CIF file of the 5-fluorouracil. So we perform for the first CF file of the 5-fluorouracil. This is unit cell lattice formed and this is the energy window obtained after performing the calculation for the first CIF file. And the lattice energy calculated will be minus 81.25 kilojoule per mole. And then we calculated for the second polymorph. This is the unit cell lattice for the second polymorph and this is the energy window obtained. And then by calculation we obtain the lattice energy as minus 57.85 kilojoule per mole. As we can see, the lattice energy the first polymorph is more negative. And we know the more negative lattice energy, more will be the stability of polymorph. So first form will be more stable as compared to the second polymorph form. Then we calculated the lattice energy corresponding to the pyrene structure. And this is the unit cell lattice formed for pyrene. And this is energy window obtained corresponding to the pyrene. Then by calculation, we get the lattice energy of pyrene as minus 31.75 kilojoule per mole. And then we calculated the pi-pi stacking interaction energy for the pyrene molecule. Then we took the two ring such that electron clouds of the two ring interact to form pi-pi interaction energy and the energy window obtained here, and then we calculated the pi-pi stacking interaction energy as minus 13.1 kilojoule per mole. And then we have to calculate the contribution of pi-pi stacking energy in lattice energy of pyrene. Then we divide the lattice energy by we divide the pi-pi interaction energy by lattice energy to count the contribution, and we found that contribution of pi-pi stacking energy is 41.25% in the lattice energy of pyrene. And then we calculated the hydrogen bonding interaction energy for 5-fluorouracil structure. This is the lattice form for the hydrogen bonding between the two molecules of 5-fluorouracil, and this is the energy window obtained corresponding to this hydrogen bonding energy, and we get the hydrogen bonding interaction energy as minus 70.5 kilojoule per mole. And as we can see here that hydrogen bonding energy is more as compared to pi-pi stacking energy because hydrogen bonding is electrostatic in nature, resulting from the attraction between a partially positive hydrogen atom and a lone pair of electrons on an electronegative acceptor atom. Hydrogen bonding interactions are strong and directional, and pi-pi interaction arises due to dispersion forces between the pi electron clouds of aromatic ring weaker than hydrogen bond because dispersion forces are generally less energetic and also non-directional. Thank you.